Learning goals are to learn how to collect terrain data, what's special about terrain data, how terrain is modeled as a DTM, and some of the applications. Why is it important for climate change? Well, there are lots of interactions between terrain and climate change. Topography can affect rain and snowfall. It creates distinct wind patterns. Topography has an influence on water runoff and erosion. Higher elevations usually mean cooler temperatures. And the orientation of slopes and, in general, topographic features create certain microclimates. There are many more, and it's important to learn how to use terrain in GIS if you deal with climate change questions. The word model already gives it away. In GIS, terrain is usually represented through a model, in the easiest case in the form of contour lines on the right, but we have more advanced features, even 3D terrain. How do we collect terrain data? The easiest conventional way would be to use a total station. You have a total station on a specific point where you know the coordinates and the height, and then you measure angle and distance to a reflector, and through simple calculations you get their coordinates. On a bigger scale, there is now GPS available, or in the EU, Galileo. These are positioning systems based on satellites. We have a number of GPS satellites in the orbit, and if your GPS receiver can receive more than 3 satellites, often it's 18 or 20 now, but if you have more than 3, you could already calculate your position by triangulating your positions from the distance and angles towards the different satellites. These measurements also need corrections, atmospheric correction, etc. So it's quite complicated algorithm that is behind these calculations. But with modern computer technology, it fits into smartphones, etc. today. It depends a bit on the geometry, whether satellites are well distributed or all close to each other. That would give bad geometry. You might also have noticed if there are lots of high trees, buildings, you don't get a good connection to these satellites. Then a couple other more recent developments are laser scanning and photogrammetry. These are two different techniques. Laser scanning is a technique where you use a laser scanner that's sending out a laser beam every split second and then stores the reflection. The reflection gives the distance to the point that reflected, but also its color. And you can create 3D point clouds from these reflections. It's basically like driving or flying a giant scanner across the landscape. The other way, even simpler and cheaper, is through photogrammetry. If you have multiple photos, for example from a video, you can derive the relative position of identical points in these different photos. The computer will identify the identical points, put them in relation to each other, and calculate a 3D point cloud from that. And on the right, you see our campus. That is not a photo, it's a 3D point cloud. If we zoomed in, you would see millions and millions of little points. And we created this model through a flight with a off-the-shelf DJI drone. All these techniques have in common that you first get points, elevation points, point clouds, etc. How do we derive a surface from a number of elevation points? Well, we can do that through triangulation, and a special triangulation is the Delaunay triangulation, named after a Russian mathematician. And he defined which geometries are good or not so good for the triangulation of a surface. Put it very simple, you can think of representing an uneven surface through a fisher net. the best way to get very close to this uneven surface is by draping a fisher net over it. And you have lots of little triangles, all those like in a net. And with this triangulated surface, you represent the real surface. Sometimes there's a limitation to Delaney triangulation. For example, if 2 points are on top of each other. That's the case if you have a wall or a cliff. If that happens, we need to mark these lines like a wall or a cliff through a break line. Here the black line is a break line, and these can also be incorporated into your digital terrain model. And now we send this to the computer, it's calculating, and we see the result on the right, a triangulated irregular network, or short TIN, which is representing the surface derived from the elevation points on the left. There are other possibilities to represent a surface just by the elevation points. You could represent it through a raster or through contour lines. Here you see some of these variations on an older German, from an older German source, but that's still valid. The TIN is one of the most efficient versions for computing. So for example, in computer games, usually a TIN is used for surfaces. Finally, last not least, another type of kind of terrain data is if we also have the trees, buildings, cars, people still in our model. That's the raw material from a laser scanning flight, for example. Then we talk about a digital surface model. So if you see the abbreviation DSM, it's digital surface model. If you see DTM, that's digital terrain model, which could have been a surface model, but the trees, buildings, etc. were already removed from the original data. There are certain calculations to do that. And if you get interested now into the topic of terrain, then here is a link where you can find a lot of free open data, global terrain data, mostly collected by radar missions by NASA, the American Space Agency. I mean, there are other sources, maybe even in your country, but this is a very good free global source. So give it a try, put in terrain in the Earth Data search engine, load it into QGIS and have a look. I'll see you for our next short